All right. We have a test a week from today. So that would be the 24th. Um, and uh, we're pretty close to getting to the point where you can do all the energy problems. So we'll see how class goes today and tomorrow. I think the topics are going to be all the way up through energy, but we'll see. I'm not going to make you like see stuff for the first time on Monday or whatever and take a test on it on Wednesday. So we'll see how things go. Okay. Um, if we don't get through enough material in the next couple days, then it'll just be up through conservation of linear momentum. Um, Anybody have any questions about the test? Yeah, anything in that energy set of problems will be fair game for the test. Okay, so let's go back to talking about energy. Um, and the roadmap, we talked about the dot product. Um, we use that to talk about work. I have one more thing to say about that, but we're mainly done with that. Then I'll define kinetic energy. Well, you've seen that before. I've been talking about how um, you can think of energy as just related to an object's speed, as long as we're not talking about thermal energy and stuff. And so this will tell you the explicit relationship. Once we have work and energy, we can talk about, once we have work and kinetic energy, we can talk about the work energy principle. The work energy principle is the most general equation for mechanical energy. Um, and then I'll define potential energy and I'll talk about conservation of mechanical energy, which is a more specific, there are restrictions on when you can use conservation of mechanical energy. But when you can use it, you want to because it's really simple. Okay, we're basically done with this. I mean, totally done with dot product, basically done with work. So we'll go on to the next couple after this. Um, we'll see that, we'll get to that when we get. Okay, so one last thing about work. Um, so we saw that we talked about the fact that, mentioned last time that if a force is always perpendicular to an object's path, the force does zero work on the object. Well, it sort of makes sense intuitively if you think about that increasing an object's energy is speeding it up, decreasing its energy is slowing it down. Um, if something's moving, if a train's moving along a track and you at one instant apply a force perpendicular, you're not speeding it up or slowing it down. Speeding it up and slowing it down would be related to the direction it's moving. You know what I mean? You're just trying to knock it off the track. And so as long as it stays out on the track, its speed isn't affected. So if at every single instant the force is perpendicular to the path, it doesn't do any work. It doesn't change the speed. There are two excuse me. There are two important cases of this. Okay, I'm done, I think. The first one is the normal force for an object that's rolling or sliding. So let's think about a sort of general case. Imagine this thing rolling along a path that isn't constant, but it's just rolling along this path. At this instant here, the normal force is perpendicular to the path. The path changes direction once you get, say, down here, right? But once you get there, the normal force is perpendicular to the path there. You get here, the normal force is perpendicular to the path. So at every instant, the normal force is perpendicular to the path, even though the path is doing weird stuff. And so that means that in any problem with a normal force, any rolling or sliding problem, you can skip calculating the work done by the normal force. Okay, so when you're trying to add up the total work done by all the forces, you can just forget about that. Even though it's a force and it can be a big force and whatever, it's doing no work because of this property. And that's like the greatest thing ever since the normal force on sliced bread. And the reason it's so great is because that comes up in so many physics problems, and we can just forget about that thing when we're doing energy calculations. Yep. Yes, but the math can be complicated. So, like, imagine that, that line integral example that I did, Yeah. So, to do a line integral like this, you'd have to figure out a way to represent that function, that curving function, and you'd have to figure out a function to represent a normal force, and you'd go through this whole integral. When you got through all that, you'd get that the work was zero. It's much better to just be able to say, forget the line integral, no matter how complicated it is. I know that normal forces don't do any work. Think about how many problems we've done that have objects rolling and sliding and have normal forces. This is going to help us really very often. Okay. And then the second type is centripetal forces in circular motion. So any force toward the center of a circular motion, and that comes up pretty often too, not as often as normal forces. So think about a case like this where you have um, an object moving around a circular path. Think of a pinball sort of connected to this post by a cable, and it's going around this circular path like this. The force applied by this cable is a tension T. But if you think about, from above, there's the circular path, here's the cable, the tension is like this, the velocity is like this. Those are perpendicular to each other. And so even though the direction of that cable tension is changing the whole time and the direction of the velocity is changing the whole time, you don't have to worry about calculating the work. This must be tension, the work done by the tension. Okay, so let's think about the forces that are acting on this ball at this instant, and think about all the work done on this ball. What kind of energy change? Yeah, it's rolling along. It's rolling along like a glass surface or some frictionless surface. Okay, so otherwise that cable couldn't be horizontal like that if it wasn't being supported from below. It could get closer and closer the faster you spin it, but it would never get totally horizontal. Can you picture what I'm talking about? If it's slow, it's going to be hanging down. If you speed it up, it'll start rising, but you can never make it horizontal. Okay, so what forces are acting? Like if you drew a free body diagram, weight force, that's going over here, that's going into the page, right? Normal force, that's over here coming out of the page. And then the cable tension. So there are three forces. The normal force never does any work, right? This thing's rolling or sliding, right? It's in that category. And so it doesn't do any work. You don't have to worry about that. This force that's always pointing toward the center of the circular path never does any work, so you don't have to worry about that. The only one we have to worry about here is the work done by gravity. And so what's the relationship between, what's the angle between the weight force vector and the velocity vector at each instant of this path? 90 degrees. So in this case, you don't have to worry about that. That doesn't do any work. In other words, with this setup, from looking at this setup, what's the change in energy? 0. Yep. And so you know that with this setup, we're assuming frictionless and stuff. So we know that the speed of this ball is going to stay constant without even doing any calculations. That's kind of cool, right? I mean, it's sort of a cool in the way of like things that you have to learn and study, as your mom says. Okay. Now that we have that, now we can go on to the work energy. Oh, no, we can't. But now I have to define kinetic energy. That'll be fast. Kinetic energy is an amount of energy that an object has. It's not a change in energy. So remember, work was a change in energy. This is different. This is like how much energy does that thing have at this instant? Um, so it's not a change in energy like work. We expect it to be related to the speed. And the formula is the kinetic energy of an object. I'm going to call it fancy T. Is equal to 1/2 times the mass of the object in question times the speed squared. And if you have the velocity vector rather than the speed, you can also think of this as 1/2 times the mass times the x component of velocity squared plus the y component of velocity squared. Because the Pythagorean theorem, the magnitude of the vector is the square root of the sum of the squares. So for example, bowling ball has a mass of 7 kilograms. And it's moving, let's say, 10 meters per second. What's its kinetic energy? The kinetic energy is equal to 7 kilograms times 10 meters per second squared. So that's 700 kilogram meters squared per second squared, and that's 700 joules. And dang it. Thank you. Okay, and that doesn't have any direction because energy never has direction. It's not a vector, it's just an amount. Okay, but it tells you something about how fast it's moving. So now, a car? Yep, and it has a lot more energy. And by the way, like the magnitude of momentum, this isn't exactly the same thing because we have the factor of 1/2 and we have the speed squared. But like the magnitude of momentum, kinetic energy says how much it would hurt for the object to hit you. Feather, bless you, a feather moving at 20 miles per hour has less kinetic energy than a car moving at 1 mile per hour. And so it would hurt more to get hit by the car. You can also think of it as like football coaches, I mentioned this with momentum, are looking for kids who can generate a lot of kinetic energy. You know, kinetic energy is how hard it's going to be to stop something. You can think of it that way. Okay, so you'd like to have a small kid who runs really fast is pretty good. A really big kid who runs really slow is pretty good. But a really big kid who runs really fast, that's what the football coach really wants, you know, because it's hard to stop them. Okay, so now finally we get to the work energy principle. Um, and this is general, which means that as long as there are no changes in thermal energy, I should say no big changes in thermal energy. There are always some changes in temperature and the work energy principle holds. So in all the kind of problems that we do, the work energy principle, you can use it. You never have to worry about whether it doesn't apply in this case. And the work energy principle says total work done on an object is equal to the change in kinetic energy. It's so simple, and so W total is the sum of all the work done on the chosen object and the change in sorry, that's not temperature. The change in kinetic energy is, you can think of that as the kinetic energy at the later instant minus the kinetic energy of the object at the earlier instant. Okay, just see how much it changed, see how much it is at the two instants and subtract, and that's equal to the total work. Um, okay, so let's say you have a block. Well, let's make it a cart so there's no friction. Let's say that this angle is 20 degrees. And let's make the mass 2 kilograms. And let's say that this cart rolls down the ramp a vertical meter. Okay, so in other words, it starts at this spot, ends at this spot, and this distance is 1 meter. start the test. What's the final speed? Now we could do this problem before. We could do it using Newton's laws, draw the free body diagram, come up with the forces, figure out the angles, figure out, you'd figure out the acceleration of the cart, and then you'd use the constant acceleration equations to, you'd figure out how far it had to travel, use the constant acceleration equations to figure out the change in speed. But look how easy it's going to be using this energy approach. So let's think first about what forces are applied. So just a general free body diagram. I'm just doing this to make sure we don't miss any forces. There's a weight force of 9.81 times 2, so 19.62. And there's a normal force. The total work is the work done by the normal force plus the work done by gravity. Well, this is a rolling or sliding problem, so this one always goes away. Okay, so all we have to do is figure out the work done by gravity. The weight force, that was this stuff. So in rolling or sliding problems, the work done by the normal force is always 0. It's always 0. Okay, so the weight force is constant. And when you have a constant force, you can just calculate the work as the dot product of the force and the displacement vector. Right? Remember that? So the work done by gravity is equal to the weight force, 0, negative 19.62, dotted with the displacement vector. Well, we could figure out what the horizontal distance is. We could figure out what this distance L was. But let's just put it in for now as L. You're going to see it doesn't show up. So we don't even have to waste our time doing, using trigonometry. So this is going to be L. And what's the Y component of the displacement? It dropped. Yep. So remember that displacement vector is the vector from the start to the end. So that's the displacement vector. And so this has to be -1. And so that's 0 times L, so that L doesn't matter, plus negative 19.62 times -1. And so you get positive 19.62 joules. Yep. So what? We can just use so when we do Newton's laws on rolling and sliding problems, we always want to use that funky coordinate system. So then we have to use cosine and sine to figure out the weight. That's just a tool we use because it makes stuff easier. With the energy methods, we're just going to use a regular coordinate system. A good question. I sort of glossed over that. So uh, in this energy approach, there's no reason to switch the coordinate system. Okay. So this is the displacement vector. Okay. So just think about the components of that vector. It's going to go some, it's going to have some x component of displacement in the positive x, and the y component of displacement is -1. You can think of that vector as you go 1 in the negative y direction and then L in the positive x direction.
Yeah, if like the inclination, like if it's going like that, have like positive, that'll be 1, right?
Yep, that's right. So this is equal to the total work. Okay. And then the work energy principle says the total work of 19.62 is equal to the change in kinetic energy. And that is the kinetic energy, the 1/2 times the mass times the speed at the bottom at the second instant, minus 1/2 times the mass times the speed at the top, which we said was 0. And so this says that 19.62 is equal to v squared and so the speed at the bottom is plus or minus, I think that's 4.45. It's a speed, so it has to be positive. So even though this was the first example that we did, and I was talking through it really slowly and whatever, it still took considerably less time to come up with that answer than it would have using Newton's laws. Like imagine all the steps of using Newton's laws. Not every problem is like that. It sort of depends what the question is asking for. But there are problems where this can save a huge amount of time. Any questions about that?
So the 0 is basically the beginning of it.
Yeah, it says that it starts at rest. So at instant 1, the speed is 0. Now let's do a similar problem. So let's say we have a 20-degree incline. We have a block on the incline with a mass of 2 kilograms. And it's going to slide down the ramp a distance of 1 meter. And now we have a coefficient of friction. So slides down the ramp 1 meter vertically down, the same as before. And the coefficient of sliding friction, of kinetic friction, is 0.1. If it starts at rest, What's the speed at the bottom? All right, well, go through the same process, and this friction is going to make things quite a bit more complicated. Um, so free body diagram, just to make sure we don't miss any of the forces that we have to calculate the work for. We have a weight force. We have a normal force. And the object's moving down the ramp, so the friction force has to be up the ramp, this direction. And that's going to be the coefficient times the normal. Work is going to be the work due to the weight plus the work due to the normal force plus the work due to the friction force. The normal force still doesn't do any work, so we can get rid of that. But that doesn't mean the normal force is 0. So we're going to have to figure out what that friction is. Okay. So we're going to have to figure out the force of friction. Okay. So that's way, way worse. Okay, so how do we figure out the force of friction? Well, for this one, now if we're going to figure out the force, we're going to have to choose that rotated coordinate system, go through Newton's second law, do all that stuff just to figure out the force. And then we'll go back and do the energy stuff. Okay. Bummer. What? Okay, good. I like your attitude. I thought you were going to be like, that's bullshit. I'm not doing this. Yeah. Yeah. Okay, so there's our free body diagram. So Newton's second law says negative 0.1 and 0 plus 0 and plus, what's the angle in that rotated coordinate system for that weight force? 20 past 270, you could think of it as negative 70, or, well, you can use SOHCAHTOA with 20, or you can use cosine and sine, of 290, or negative 70. So 19.62 times cosine and sine, if I'm going to call it 290. And all that's equal to the mass times the acceleration. The good news is all we need to do is calculate n, because then we can just plug it in here to get the friction force. So the y equation says n is equal to negative 19.62 times the sine of 290. Can someone tell me what that is? And then the negative sine of 290, yeah. What was it? 18.4. Okay, and that's newtons, and then we can plug that in. All we want is this, so all we needed was N. So the force of friction is equal to negative 1.8440. Okay. Now we're going to have to figure out the we're going to have to figure out how far it travels. Like now we need to represent our displacement vector in this coordinate system so we can use our force vectors. Right? So we need to figure out what this length is. So let's get the displacement in that rotated coordinate system. We know it's just going to be in the positive x direction. So we have a triangle with a height here of 1 meter. This angle is 20 degrees. And we want to figure out this distance d. So 1 over d is equal to sine of 20 degrees. So that d is equal to 1 over 0.342. What do you get for d? 2.92 meters.
Reference to the problem on force friction. Is it supposed to be 18.44 instead of 1.8?
That was the normal force, and then our coefficient of friction is 0.1. So we have to multiply the normal by 0.1 to get the friction force. Now the displacement is just positive 2.92 in the x direction, 0 in the y direction. That's in the rotated coordinate system. Okay, well now work done by gravity, we can do it by multiplying. So what's 19.62 times cosine of 290? 6.71, negative 18.44, right? That was the weight force. Dotted with the displacement vector. So that's 6.71 times 2.92 plus negative 18.44 times 0. And you get, that should come out to just be 19.62, like it did before, because it's the same displacement and the same weight force. This is the weight force in the rotated coordinate system. That's 19.62 times cosine of 290. And now finally, the reason we had to take this bad detour is the work done by the friction force is the friction force vector, negative 1.8440, dotted with the displacement vector, 2.920. And that's equal to negative 1.844 times 2.92 plus 0 times 0. And what do you get for that? Negative 5.38 joules. So the total work is 19.62. That's the energy added to the system by weight. Minus 5.38, that's the energy removed from the system by friction. And friction always takes away energy. You never increase the friction and have something take off faster, you know. And so you get 14.24. 14.24 joules. And so finally, the work energy principle says 14.24 is equal to 1/2 times the mass times the speed at the end, minus 1/2 times the mass times the speed of 0 at the beginning. And so v squared is equal to 14.24. What's the square root of 14.24? 3.77 meters per second, and we want the positive one. Okay, there was friction, so we expect it to be slower at the bottom of the ramp than in the case where there was no friction. And notice we got that. When it was just rolling, we had 4.45. When it's sliding with friction, it's 3.77. Let me say two quick things. So notice, first, friction always removes energy. And second, problems involving friction often get much more complicated using an energy approach. So as you're starting to imagine yourself seeing a problem that you could do multiple ways and trying to figure out the path that you want to take, if you see a problem that has a normal force in rolling and sliding, or a centripetal force like a ball swinging around in a circle, that you want that to make you think like, okay, maybe an energy approach is the way to go on this. If you see friction in the problem, that makes you think like that's sort of a strike against the energy approach. Often that's going to complicate things a lot. Any questions? Okay.